Hi guys, so today we're going to learn about Ampere's Law and Bio-Savart, which all of the three of them, Ampere, Biot and Savart, are French, and they're going to help us to figure out what is actually the magnetic fields. Okay, each one of them is always valid, but sometimes Bio-Savart is going to help us more than Ampere, and Ampere going to be a more useful equation instead of Bio-Savart. So let's move on to the first question and see which one will help us. Okay, so the first question is about the toroid. Let's draw a toroid. So a toroid is actually looking a little bit like a donut. Okay, let's draw it. So this is my toroid. Here I have a circle, here I have a circle. You see? It's like a circle with the hole inside, and I give it some height. Let's give it h, some height. And this is my toroid. I can look it from above. It's look like this. If I'm looking from above, it's just a circle with the hole inside. Okay, and okay, let's give also the geometry. This one is R, and this one, this distance is B from here to here. This is the dimension of my toroid. Okay, perfect. And the thing that I'm adding here is I'm taking a wire. Okay, let's do it in different color. Let's do it in purple. I'm taking a wire and I start to coil it around the toroid. So I take one wire here and here, and I toroid and do another cycle, and another cycle, and another cycle, and I can continue doing that until I have many wires surrounding my toroid. And actually in this side I should see also them go down, right? So it's look here, I don't see anything. It's going inside the hole, I don't see it. And how it's look from above, it's look like this, right? And another thing that I do is I passing a current through this wire. In which direction? I do it in that direction. I do it that the current going here, and go inside. So which mean from here I have it's coming out at me. Sorry, it's coming out at me, and then it's going inside in all direction. This one is also like this. This one is also like this. They're all the same. Okay. And the first thing I want to ask you is, what is the direction of the magnetic field? What? Let's do it above. What is the direction, right, of B? What is it? Actually, other way to say it is, what is the direction of B? And I also can give the axis. Let's give this, let's make, it's not good that I do it in this line. Let's do this one as X, this one as Y, and the radius, let's go from here. This is R, and this distance is B. It's a small b because we're dealing also with magnetic field. So I did small b, not capital one. So what is the direction? So let's cut. Okay, let's cut this toroid. And if we cut it, we actually have like this kind of figure, right? This is the toroid. If I cut it and look inside what's going on, this is B, remember? This is the height, H. That's how it looks like. And what I have here, I have a wire around this one. And the wire going in which direction? It's going in that way, and that way, and that way, and in that way to start the new one. Okay? And now I'm going to introduce to you the right hand rule. And maybe you are confused because you said, hey, you introduced it previously, so what's going on here? You have another one? Yes, I have another one, another hand rule, which clear that. The thumb actually going to show where is the current is going, and the fingers, how they curl up, is how the magnetic fields curl around wires. So I'm gonna take my thumb, I'm gonna put my hand on the wire, be careful not to be electrified, okay? So put it in the direction, I can see what is the magnetic field around this wire. So I have to draw magnetic field in red. So if I'm going here with the wire, I can see that I have here it is, the magnetic field going inside. So inside it's like this. And when I look here, I can see that the magnetic field definitely pop outside of this frame, right? Let's go to the other part of this square. If I'm taking my hand with the current, I can see that from here it's again going out, and here it's going inside. And if I'm going here, again it's going this direction, right? And here I finish the circle, I want to get inside here. So this is an X. And when I go with this wire, here I'm going 2, and here I'm going out. So what you can see already, that here I have a huge concentration of magnetic fields, right? And in the outsides, maybe there's some distribution, but it's small compared to that. Why? Because I have how many coils do I have? I have a lot of them. And think about it, that each coils give a lot contribution to the inside. So I can actually neglect the effect of magnetic field outside, right? Because I have this all over the place in each one, and they all contribute to each other, right? So that's the idea here. So I can already say that the magnetic field is actually inside this toroid, okay? Inside this donut. You know, you have donut with cheese, we have donut with the other stuff, with the jam, but this donut is actually loaded with magnetic field. And this is one of the ideas of coils in general, which you're going to talk in the next to come tutorials. But you can see here that I have a lot of magnetic field. So I can already state as a magnetic field, if I cut this part, let's say that I have another color, perfect. So let's say that this part is actually this part, okay? So what I notice here, that the magnetic field is actually pointing in that direction, right? If I'm gonna cut it here, you're gonna point in that direction, and that direction, and that direction. So in which coordinate the magnetic field is? If this is theta, I want to remind you, this is theta. Theta is to go up from the x-axis. I'm actually going against theta. So I already know that the magnetic field, B direction, is equal to minus theta. Okay? So this is the first thing I want you to understand. What is the direction of B? This is the direction. So we found that. Let's move on to the next part of the question. So the next part of the question is actually calculating what is the magnitude of B. And I want you to notice something, okay? Do you see that here I have some symmetry, okay? When I look at this, the angle does not tell me anything. If I'm in this angle, or at this angle, or at this angle, or this theta, or this theta, or this theta, or this theta, there's actually no difference. I have some symmetry. Remember when we deal with electric field, okay? So we talked about when we have symmetry, we can actually use Gauss's law, right? So right now we're gonna have some equivalent idea in the magnetic field. And it's gonna be really comfortable because it's easier than Gauss's law. And this idea is Ampere's law. Let's talk about Ampere law. So what does Ampere law says? Here it is. This one is perfect for us. So Ampere's law is really it's really similar to Gauss's law. Let's draw again Gauss' law, okay? So Gauss' law said that if we have some volume, this is the volume, and the surface of this volume, the sphere of the volume, not the sphere, but the surface of the volume, if we decide about sphere, so it's the shell of the sphere. I'm taking this one and I'm taking E, the electric field. I do dot product between dA, and what is dA? dA is the element of the surface of this volume, and Gauss's laws state that this one must be equal to all the charge, let's do sum of the charge in A, inside A, divided by some constant. This was Gauss's law. Now we're going to draw Ampere's law. And I never saw this comparison before, but I think it's so obvious. It's so nice to use it. So right now I also gonna have integral, but it's gonna be a line integral, okay? But let's do it like more clear. What do I mean by a line integral? Okay, now I don't need a surface integral. I want to have a line, dl, okay? And it could be whatever I want. Let's find something. Oh, perfect. My guitar cable, it's perfect for this mission. So I can choose whatever loop, whatever line that I want. This, for example, I can take this one and put it. But this line must be closed. It cannot be open. It can actually do a jiggly stuff. It can be like this. It can be a perfect circle. It can be a square. Whatever I want. Just need to start, go somewhere and finish. That's all. So I decide about the line. This is the reason I'm going through this line. This is dl, this is a vector. And here inside, I'm gonna have B, the magnetic field. And I'm gonna do a dot product, okay? And here what's happened, what I have inside this loop, I have some area. Think about it, that if I have a strange loop, doesn't matter, a square, a circle, a trapezium, it doesn't matter. And I take this and put it in water with soap. And I take it out. What I have? A bubble, right? So that's the idea. Here I have some bubble, some area. It could be crazy, it could be with this kind of shape, it can be whatever I want, but I have here some area. Here remember that we had a volume. Right now it's an area, okay? This is a 3D problem. And this is easier. This is a 2D problem. Okay, I want you to keep that in mind. So, and what this is equal? Here I have constant. This constant actually presents the electric field. In magnetic one, we also have a constant, which is mu 0. And right now we're not going to talk about charge. Remember when we did a comparison with the forces, Lorentz force, we actually deal with moving charge. And moving charge is actually a current. So here I'm going to have sigma of I penetrate. Okay, I pen. And what the idea of I pen is actually only the currents that actually poke my surface, this one. For example, oh, this is a perfect example. So let's say that I choose this line, the square line, and right now the whiteboard is actually my surface. And if I take this pen, I can poke this surface and go through the other side. This is gonna be something to contribute to here. And what is the negative sign is if somebody comes from here. So you need to decide what is the direction which is positive and what is the direction that is negative. But you see the comparison between them. I can even take it farther and said, and that's what you're probably gonna see in your homework. I can see that this one is actually equal to what? 1 epsilon 0, and here is the charge density, right? I can take it to the volume idea, J dV, rho dV, the charge density, right, of each location. And here I can do the same idea. I can put mu f as here, mu 0 here, and put an integral. This is the integral of, remember, what is I is actually J dA. So this is a two-dimensional problem. So you see the comparison, let's do it like this. You can see how they are related to each other. So that's also what Maxwell saw. But we're going to talk about that in another chapter. So right now I'm going to keep that with me. So I want to remind you that we're actually dealing with finding the magnetic field. So let me clean this one a little bit. So I want this drawing actually. It's going to be nicer to deal with this one. So here and here and here and here. Perfect. So we have this, the hole inside. We have the end, right? We have this axis and this axis. And they actually ask what is, let's clean this also, it's not relevant. Now it's what is the magnitude, magnitude of B, right? So we know already that B going in that direction, okay? So we know something about the symmetry. We can use it. We know the direction. Sorry, let's do B in red because I love to put it in red. Red, red, red. So if I want to use Ampere's law, here it is, Ampere's law, I want to decide about a loop. So it's obvious that I'm gonna choose this one. I said it's obvious, it's not obvious, I just, you know, more experienced than you, so I can say this. So I'm gonna choose this loop, which is in distance r from the axis, okay? And let me clean this one. And so let's draw what I actually have. I actually decided that my loop is gonna be an integral of this surface, you see it? This one. And I decided that the direction of the loop is with the magnetic field, also in minus theta. So I have here B, right? Which has some magnitude, right? And also it's in direction of minus theta dot what? Dot dl, which is also in the direction of d theta, okay? How I can describe this magnitude of dl? This is dl, and this is b, the vector. I can say that dl is actually r d theta, right? Sorry, this r, it's a specific r d theta. And b is a function of l, right? So I can actually take b. Okay, let's do it more organized, okay? I do it from the beginning, okay? And so, first of all, let's talk about the angle. So if we're gonna do a dot product between the two of them, they have the same angle. So actually, the dot is die because the angle is 0. So cosine of 0 is 1. So I can get rid of it. And I know that the magnitude b is actually a function of r, right? It depends how far I am from the wires that I have. So it's a function of r, so I can take it outside. So I know that b is a function of r equal to the closed integral of dl. And what's this one? This one is actually asking you what is the length of the line, right? So the length of the line is 2 pi r, and it's coming from the reason that this actually dl is r d theta. R can go outside, and if I'm gonna do integral of all the line from 0 to 2 pi, I'm gonna have r 2 pi from the integral. So I know that the right hand side of the equation is equal to 2 pi r b r. That's all. Now I need to ask the second question. Remember that I always divided this equation to two parts. We found out what's this part, but we didn't find out what this part. So which currents actually poke my surface? So let's draw my surface in a more comfortable way. So that my surface is actually this one, okay? In the middle of the toroid, I put this thing, okay? And remember the current that we actually coil all the wires around the toroid. So I coil it here, and here it's coming, how I drew it, it's coming out, right? This one, actually it doesn't matter, but this one is coming out, and this one going in, right? So this one gonna poke my area, my bundle. And this thing happened also here. And this thing gonna happen also here. Everywhere, that's what happened. Go back, pocket, go around, and start the next loop. That's the idea. So I can say that this one is equal to what? To the constant, as the equations say, and the sum of all the penetrate one. And which one penetrate? This one, right? The one that's going inside. And how many of those I have? As many as coils that I have, which we said it's a given, it's n. So we can put here mu 0 n I x equal to pi r b r. If we're gonna rearrange this equation, we get to the final result, which states that b r equal to this one divided by this one, mu n I divided by 2 pi r, and remember this one in direction of minus theta. So we found the magnitude of B. But we talked about the magnitude of R. It is actually look up between R, capital R, and R plus B, right? The end of the toroid. Let's try to check Ampere and find out what is actually the magnetic field, outside, okay, outside of the toroid. Okay, so let's say this thing stay the same. Okay, let's do it. Why say stuff? Let's do this. Okay, so I don't need this equation anymore, right? Let's clean it. Okay, so right now I have this toroid and I have this hole. I have my axis, and right now I'm going to choose this line. Can choose it, whatever I want. And right now this is my area. Okay? Do you see it? And the magnetic field is gonna be the same. The magnetic field, as before, is a function of R. It's gonna go out. This integral is 2 pi r, just my r is changed to a bigger one. It's okay, I can do it. Now I want to ask you, this equal to what? To mu 0, the sum of all the currents. Right now, what do I have? I have some currents that actually getting out of here, poke my area, continue here, and then poke my area. And again here, and again here, and again here, and again here, all over the toroid. So this one is actually, I have n that going in this direction, plus n that go in this direction. And they are the same magnitude. It's the same, right? It's the same coil. I just continue the same wire. They have the same current. But you see that these two have a different sign. One going inward, and one going out of the area, okay? So they actually cancel each other because they have the same magnitude but different sign. So that which clear that this one is equal to 0, can divide by this constant, and they're getting that the magnetic field outside of the toroid is actually equal to 0. Okay? Next question is, what is the magnitude inside the hole? Okay? Let's find it. So again, draw it again. So this is the toroid, this is the hole, right? Let's do the hole a little bit bigger. This is the hole, and right now I'm going to choose this area. Okay? This is the area that I have. And now what I can see, what I can say that again the same thing. I'm gonna get that it's not cancelling out, 2 pi r. This is what's going on with the right hand side of the Ampere equation. But right now here, what can I say? I have a current that go out of here, going this direction, and go inside here. Is not poking my area. There's no, even this one and this one not touching my area. Nobody come and try to poke it. So actually this term is equal to 0 because I don't have anything inside. It's like in Gauss's law when I don't have charge locked up inside my volume. So I can say that the flux is equal to 0. It does not mean that the magnetic field, the electric field is equal to 0. Like here, it doesn't mean all the time that B is equal to 0, the magnetic field. But here in this specific case, I can just divide by 2 pi r. I succeeded to take BR outside of the integral, so it's okay. And I can see that also outside, BR equal to 0. So we actually found the magnitude for B in all the space, right? In all the flat space that we talked about. We have it outside 0, in the hole 0, but inside the toroid we had some magnitude which we calculated. Okay, perfect. So this was a classic example to use Ampere law, and now we're gonna continue to the next question, which gonna actually teach us a little bit about Ampere and also about Bio-Savart. So let's clean the board. So the second part, the next question. Okay, so I don't know if you know that, but Earth itself, the world, this is the Earth, this is, say, America, Europe, right, Africa, this is the world. The world is actually a magnet. Okay, you have the North Pole and the South Pole, and the magnetic field lines going like this. So we have a magnetic, here it is, magnetic field, and here's the sun, right? The sun is really dangerous, put our sunglasses on it. Smiling sun, right? Okay. And there's a lot of dangerous stuff in space. For example, meteors and other stuff, burning stuff, crazy stuff, but they also affect by this magnetic field. If they have a charge and they're moving in some velocity, remember that we talked about Lorentz force, so they're gonna actually go around the Earth, okay? So this magnetic field, the radiation and stuff like this magnetic field is actually saving us. And it's one of the reasons we have life on Earth. And if you think that Chinese people discovered the magnetic field with the I forgot the name, how it's called, Mlpen in Hebrew. This thing that tell you where's the north. I would like if you in the comments you're gonna write compost. Not compost. Never mind. Something like that. So north and south. Okay, write in the comments below how you say this device to tell you where is the north. Okay, and the one that discovered it before the Chinese is actually animals. For example, birds. Birds using this magnetic field to navigate in the world when they're moving from a continent to other continent. Okay, so they have inside of them this magnetic field detector, and right now we're going to do a question about a scientist that want to explore this idea. So what he actually did, he put a wire. This is a wall, and this is a really long wire, with the current I, and he put some bird close by, some chicken little. Okay, so let's have like here is the bird. This is a, let's say that it pop out of the egg. It's a really small and cute bird. Here it is. Okay, in some distance R, okay, from the wire, and the wire compared to the egg is so long. Okay, the wire L is 10,000 times from this distance R. Okay, so I can use also Ampere's law. Okay, that's about the question. The question is, what is the magnetic field? Okay, what is the magnetic? What is the the magnitude of? No, you know what is actually B? Let's find it as a vector. Okay, so we can use again the right hand rule, right? Put it on the wire. Be careful not to be electrified. And I know that the magnetic field is actually going around this wire. This is what the right hand rule, the first right hand rule, and the one we learned in the previous one is actually called the second one. So it means that the B, the magnetic field, is actually coming inside here and going from the other direction. That's what he said. Okay. So how can I find that? I can use Ampere's law. Why I can use Ampere's law? Because I can see here a cylinder symmetry, infinite cylinder symmetry. Why cylinder? Because you can think of a wire of being a really small, tiny cylinder. So we're going to use the same loop that we used before. We're going to do a circle. Okay. I know that the magnitude B around this circle is always the same. It's a function of R. I know that, of the distance. And right now I can use Ampere's law. So what Ampere's law states, it says that the integral in the closed line of B dl, which I choose to be circle with some area, and dl is equal, this one must be equal to what's penetrate, mu 0, and what's penetrate is only I, this current. So only this I, and this term is actually B can go outside, is a function of R, and this is a constant, right? It's r d theta, and I'm running on theta. So this is 2 pi r as before. And right now this is a really important equation that I'm sure that you saw in the lecture. So b as a function of r is actually equal to mu 0 I divided by 2 pi r. So this is the magnetic field produced from infinite wire, okay? Infinite wire, which means the length of the wire is so significant compared to the distances from the wire you are taking care of. Okay, so this is the idea. Okay, perfect. And something that I want to say, it's this may be r, but we're actually talking about the distance from the wire. It's not r the radial. It's not must be r the radial one. It's just the one that away from the wire, radially away from the wire, but not radially off your system. You're gonna see it next. And what's happened to the scientists is actually that the bird didn't move at all. They didn't care. So he thought to himself, maybe I use a really weak magnetic field. So what you can do to increase the magnetic field, if you look at the equation, you can come up immediately. You can say, aha, I can take the current up. I can say that the current is stronger. The current is stronger, right? So the magnetic field is going to be strong. But the scientists use the maximum value he can use for the current. So he cannot do it. So what else you can do? You can you can move the wire close to the bird. You put the bird close, put this chicken little close to the wire. But it's a problematic, the chicken little doesn't want to move, and this one is connecting to the wall, so he cannot do it. So what else he can do? Actually, he can take this wire, let's do it again, and curve it. What do I mean by curve it? We can take this line, here it is, this is the wire, this here gonna be X and Y, here is the bird in the middle. It's only the head of the bird. This is the bird, right? And right now it's gonna curve it around. So the current going in this direction, and this direction, and this direction, around the bird, okay? And he stated that this is gonna increase the magnetic field. Okay, let's find out if it's gonna happen. So, right now, let's calculate only this part. B of the curve, I can do BC, okay? BC, only this part. Let's calculate what is the magnetic field of this one. So if I look here, I can say that the magnetic field is actually what? Is poking this bird, right? So it's inside, it's in this direction, from every point here, thanks to the right hand rule. Okay, so I know the direction, but I don't know the magnitude, and I don't have here any infinite symmetry that I can use, or any symmetry with the Engel stuff, nothing I can do. So here, remember what we had in the electric equation? We actually had, I'm gonna remind you, let's clean this stuff, okay? So what we have Coulomb's law, which said that the electric field, let's say a small contribution of the electric field is equal to what? First of all, to a constant, right? 1 over 4 pi epsilon 0, right? Which one can say it's just k, but it's the same idea. Multiplied by what? Multiplied by dq, right? And divided by r3, r in the power of 3, and in direction of r. That's what we have previously, remember? So right now we're gonna have something really similar. And this is a vector, right? So right now this is a magnitude of the r. So right now we're gonna have Bio-Savart. And Bio-Savart states something pretty similar to it. It states that small contribution of magnetic field from a part of a wire is actually equal to constant. Familiar, constant. So it's gonna be mu 0 over 4 pi. And remember that we are not dealing with dq in magnetic field, we're dealing with a charge that is moving. So we're actually gonna say that it's a I moving charge, right? dq to the dq, then let's do idl, okay, and I'm gonna in a second explain it. Idl, which is dq dt multiplied by, sorry, so if I'm gonna think about that, v multiplied by dq, v is actually dl over dt, and dq over dt is I, so we actually have idl. So this is the concept where it's coming from. So idl, and here down there I have al, I'm gonna call it rdb, okay, in the power of 3, and here cross al db, as we have, let's do it, we can do it, just het, okay? So it's the same concept, you see? You see how similar it is to the electric one? So this is the concept I want you to keep in mind. It's something really obvious, and you can remember each one of them. So look that here we have like, we upgraded the level of the question. Magnetic, here it's a little bit complex, so you can think about Ampere's law as a really easy version of Gauss, and this one is a little bit more complicated because we have this cross, and we need to deal with this cross. So let's draw this one here in our example. So this part, okay, for example, only this one, how it's contribute, this is dl, okay, and dl is always always pointing in the direction of the current, okay, because it's the velocity, whereas the charge are moving, that's where it coming from, okay, so it's mass pointing in that direction, okay. So this, so let's actually do the formula. So bc, not bc but dbc, okay, the differential idea is mu 0 over 4 pi, which is just a constant, I, which also for me a constant, but then I have a dl, which is a vector, cross al db, which also a vector, and if here I did a vector, so down there I need to do al db square, magnitude square, okay, perfect. I can also, you know, multiply, I can divide by the magnitude, okay, this part, and can write it in another direction, which is r. It's I divided by magnitude, but also here, right? So wait a second, I divided this one by the magnitude, and I'm gonna wait a second, it doesn't make sense. If here it's square, okay, sorry, this one is hat, and I can also write it in another form, which is rdb multiply this by the, and rdb as a vector, okay. Sorry, I can write it this part as I want. You can multiply by the magnitude or divide by the magnitude, both of them are completely fine. So you have this equation, and the way to solve Bio-Savart is actually to understand who is dl and who is rdb. If you know both of them, you're done. The question, easy peasy, piece of cake, okay, super easy. So let's state which one is what. So dl is actually a small line in the direction of the current I. Okay, that's all what dl is about. So in our case, dl is actually, if I curve this one in a magnitude L, so it's actually dl is equal to what? To L d theta, and it's go against theta. Remember, this is theta, so you see the current going against theta, so it's minus theta. This is the direction. Easy. 50% of the question is yours. Next one is to understand what is RDB. So RDB is actually is where DL is actually start at DL, and it's looking, that's how I imagine it. I think you have like a goggles, and it's looking for the interest, the point of interest. It's looking where you want to calculate the magnetic fields. You see? It's looking in that direction. So the magnitude of RDB is actually L, right? But the direction is minus you see, because I'm going to this location, not to this one, this one. If we're gonna go outside of the axis, it's gonna be plus r, but if we go against it, it's minus r. So we found the two main players of this equation. So what's left is to do the math, okay? So this is not the hard part of this course, okay? Because you need to know this one. So I have the famous do r, theta, and z, right? So the famous cross circle. So if I'm gonna do dl cross r, right? You see? So it's minus theta and then r. So we can forget about the minus sign, right? It's a plus, but it's first it's theta and then it's r. And I'm going against the clock, so I'm gonna have z with the negative sign. So actually dbc, each contribution, dbc, is equal to some minus z direction. And the value of it is, first of all, mu 0 I 4 pi divided by, this one is r square, right? R square, this is the size, r square. Yes, r square. And yes, and here I have RdB, right? And RdB is let's go to this one, okay? So it's r third, right? And here I have yes, I confused that a bit. Okay, so this is r3, and first of all I have dl, which is rd theta, and then cross, okay? I can take this one. I'm gonna write it bigger, okay? That's the reason it's confusing. So dbc is equal to the constant mu I 4 pi, and in the denominator I have this one, which is r square, right? Let's do r third, r3, this configuration, and then I have dl. And here when I this one, I meant that this part only changed to this one. That's the idea. You can choose whatever it's comfortable for you. Right now I have dl, and dl is rd theta, and I have here, if I choose this configuration, I must put here r, and I know that this is going to be in the minus z direction, so I can see that r cancels with this one, and in general I have that dbc is equal to mu 0 I 4 pi and over r d theta minus z. So this is the result that I have. So this is the magnetic field where the birdies were Chicken Little. Not exactly, because it's just small dl. We actually have half of a cycle to go, right? All of this. So let's clean the rest of the board. And I'm gonna say that if we want hold the cycle, so we actually need to say that b of the curved part is actually the integral of all the small curved parts, which we just found. I can take the constants out, which all of these are constant, so everything is a constant, mu I 4 pi r, and I got the integral of d theta. Okay, so what is the biggest angle that I have and what is the smallest one? So I have here, I'm gonna go off a what? Just a half of a cycle, so this one is actually pi, so pi killing this pi, and I found out the BC is actually equal to mu 0 I 4 r in the minus z direction. Perfect, so we found this part. And if you want to calculate what is the total magnetic fields, we need actually to understand, okay, so what is the contribution of this part and this part, right? And we need to do superposition and sum them up, right? So okay, let's put it here. Let's clean this one and this one. So up. Yes. So this is going to be in the minus. So right now this is actually BC minus Z, and here is B total, and we're going to do superposition, right? Superman sign. So here I have contribution of two contributions, this one and this one. So I want you to think about it like this, okay? Here the bird is looking. And at the beginning the bird was looking to the left, but and what she saw only line, only the wire going to infinity, like you at the beach and looking to the sea. You don't see the end, you see only sea, okay? It's infinite long, okay, compared to the size you are looking around you. And then it's looking to the right and you see infinite amount of wire. It's going to infinity. It's super long, okay? Of course it was an assumption, yes, okay? So this is actually have the magnitude of half of infinite line. Why? Because the bird looked to the left and see, wow, I see a line, or I see the wire. And then she looks to the right and says, oh, I see just next to me a curved line. So it's a half of infinite line, okay? So an easy way to do it is just say it's a half of B infinity, the B of the wire, right? So, but I have two of them, right? Because I have contribution from here, contribution from here. So it's actually equal to the original value that we had before. We calculated the first section of this question. So we actually increased our value by this amount. So the scientists actually, by curving the wire, actually increase the magnetic field. Okay, you could actually calculate that this one is equal to the half of the result that we have. If you want to do it more properly, you can use Bio. You can say that you have here dl, right? And here you have RdB from infinite to here, right? You can actually calculate that and found that this is the same result. But if you want know this quick way to get rid of it, so you can also do that. So you actually increase the magnetic field by curving the wire. So right now I want you to think about what we have in the first question, the toroid, which was coils, right? Also curving. So what you're gonna see in the next chapter is that by coiling stuff up, we can increase the magnetic field, okay? So that's the idea that I wanted to show you in this question. So I put you down below in the link that you have another questions which I think super relevant to the class and really good examples, because you need to practice a lot. It's not enough to do 2 questions, one in Ampere's and one Bio-Savart 1 hour. I think you need to practice more. I think these 2 ideas are really easy, okay? They're not complex, okay? Gauss's law was super complex in my opinion, and Ampere's law is like taking it down by 1 dimension. It's insane, okay? It's really easy. You just need to get used to it and to the kind of thinking. So I'll put another exercises for you to do and work, and I will open the homework. So good luck with the homework. Keep practicing. I want you to imagine more loops, try more areas, and Bio-Savart, start to find wires and start to cut them to small dls. That's all you need to do, and it's really easy as we talked before. Okay, and next chapter, next week, we're going to talk about Faraday, which you remember Newton, which was a genius, and you have Einstein, which was another magnificent genius, but in the middle there was Faraday, and Faraday was not less than 2 of them. He actually invented all the idea that we can control electricity. So it's going to be a really important chapter. So see you next week with the next tutorial. Goodbye. Good luck with the homework.